So let's try this sample question. This is unbalanced. I know automatically it's unbalanced because when I look at it, there's an acceleration. That means it has to be unbalanced. That means there has to be a force bigger than the others. And I know because it's a positive acceleration, it's speeding up. And the thing that's going to be bigger is my applied force. So I'm going to draw my diagram. I should always draw a free body diagram every time I do one of these questions. It will be a requirement, probably on tests and quizzes. It'll actually ask you for a free body diagram. So you just get used to drawing it. These two are going to be equal. We don't need them in this case. They're just there because they exist. We can't ignore them. I have an applied force. I'm making it nice and big because I know it's the dominant force. It's the thing that's making it speed up with a small friction force. Now in this case, I'm going to go farther than the diagram. I'm also going to solve for this because I know some information. I know the acceleration is 1.9 meters per second squared. I knew just from the units it's an acceleration, and it said so in the question. And I know the mass. Now the mass is 15.5 grams, and that might seem fine to use, but we haven't discussed this yet. It's important to realize base units for mass in physics should be actually kilograms. We do everything with kilograms, which seems strange, but that's what we do. So that means I need to take this number and convert it. I'm going to divide by 1,000 or move it 3 decimal places. So I end up with 0.0155 kilograms. Now that seems tiny, but remember we're talking about a toy car. It is supposed to be tiny. We're not talking about big masses here. The last thing we know is it tells us the friction force. So the friction force is a very tiny 0.020. Again, we're talking about small amounts of force. Don't forget to put your units on. Teachers love units. They make us happy. Okay, there we go. Now, when we go to do this, we need to think about the fact that we can then find the applied force. That's our goal. What's our applied force? And I'm going to write first, the force equation for this. When I think about my net force is going to be whatever's making it move forward, in this case, the applied force, minus whatever's slowing it down. In this case, we have the friction force. So that is my net force equation. I don't know the net force yet, and I don't know my applied force. That's my goal. But I know my friction, which means this is going to be important in the end. To get my net force so I can use this, I'm going to use Newton's second law. You can't forget, there's 2 ways of finding net force. So if you can't find it the one way, you can always find it the other. This is the mass times the acceleration. And we have both of these, right? We have the mass, we changed to kilograms. Make sure you use your converted. That's important, or you won't actually get a force. Forces are based on kilograms. And my acceleration. 1.9 is the acceleration of this car. This will give you the net force or overall force acting on this car. So I'm going to go 0.0155 times 1.9, and I get a small amount, but it shouldn't be big, right? We're talking about little toy cars here. 0.02945. I'm not going to worry about rounding yet because I'm not done. Last step, I'm going to go back to that net force statement I made before. I know my net force is going to be my applied minus my friction. So I can fill in 2 of these forces now. I now know this is 0.02945. I don't know my applied force. That's what I'm working on. That's what I'm trying to find. And I know my friction force. It's 0.020 given in the question. Now, when this goes to the other side, you'll notice it will become positive and my numbers will get bigger. So I will end up with 0.04945 newtons. Now, this is not my final answer because I need to think about sig figs. I only get 2 sig figs. So I'm going to round this to 0.49 before putting it in my therefore statement. And that would be the applied force. Now you think about it, that's a tiny amount of force, but children push cars, right? Toy cars. So that makes a lot of sense. There you go. All done.